This is Lab 2 Projectile Motion with Aiden KI. So the purpose of this lab is to compare the projectile motion of a small paper ball to a model with drag and without drag. And the physics principles that will be used are gravity, drag, and Newton's second principle. So the formulas that were used in this were the velocity update, position update, the average velocity, and the drag force. So these are the experimental results of the lab. Yeah, this is the experimental setup. So we took like two of these like track things in the back of the physics room, and we set them up as our like measurements. And so our system was the paper ball, our surroundings, our gravity and drag force. The measurement were those tracks that we used. And the procedure, you just record the motion of the ball after being thrown, and then use Tracker and GlowScript as your programs. So observational model, use Tracker, of course. So you add the video to Tracker, and then you use the calibration tool to measure the distance of the tracks. So it was like about a meter from where it was thrown, right there. And then use a point mass to track the motion, which you can see here. So these are the results of the observational model. The starting point was 0.004 meters in X and 1.025 in the Y. Total time it took for the ball was 0.8 seconds. Maximum height it reached was 1.53 meters. The total distance, so the distance in the X was 1.19 meters. And the initial velocity was calculated using these first 2 points, so the time at 0.033 seconds, time at 0.0 seconds, and you get 2.9 meters per second and 3.30 meters per second. This is the computational model. This was used, this is what GlowScript was used for. So basically you take the data that you got from the experiment and you add that to the GlowScript starter code. You change the necessary points, so I think you just add the fnet and then add the drag for if there's drag, and you put v to 0 if there's no drag. And then you do velocity update and position update, and that'll give you this curve here that was from the GlowScript. This is the GlowScript code, as mentioned. So you're going to add the initial position that you get, the initial velocity that you get from the tracker. Delta T was going to be 0.033 because the phone records at 30 frames per second. And then you change, like, for this one, there's no drag, so the B was equal to 0. And then you add the drag in here, add that to the fnet, velocity update, position update. There you go. So this is a comparison. The experimental's in blue, drag is in red, and yellow is the one with no drag. So you can see the drag and the no drag are really similar. That's because there's a little paper ball, so it's just not going to have much drag on it. And the main difference you can see they follow each other pretty tightly, but at the end, like the drag and the no drag, the model doesn't even go to 0. The experimental does. So some possible rooms for error. Human error, obviously. Like it's hard to pinpoint exactly everything on tracker, so that could cause some errors. As well as the measurements. Like the measurements might not be exact. It was a little hard to see like what it was on the tracks because they did have measurements, but it's kind of hard to tell here. And also like the mass of the paper ball was estimated. Couldn't really figure that out. Then technology error. That's always a possibility when using GlowScript and tracker. Additional questions? What does it mean? So the gravity and the drag model I had did not yet reach terminal velocity, and you could see that because the um, velocity graph from glow script didn't begin to taper off, so it was still increasing. Um, this is because the drag is so low compared to the mass, so a net zero force hasn't been reached in the time that it was thrown. So to get terminal velocity, the ball would have to be falling for longer. And then if the ball was thrown straight up, it would take the same amount of time to reach the ground. It's because the forces acting on the ball in the y direction would be the same.